Now in this video I will simulate the behavior of a simple pendulum under different initial conditions. The equation of motion, the nonlinear equation of motion of a simple pendulum is given here. I will start by modifying the equation of motion or rearranging it so that the acceleration is on the left hand side of the equation and the rest of the terms on the right hand side. And I will start by planting my state variables using two integrators. Connect the integrators. The input to the first integrator is the acceleration. Let me call it ddq for theta. And the integration of the acceleration is velocity dq, and the output is the angle theta. I'm going to call it q. Now the acceleration is equal to a negative constant g over L times sine theta, so it's a function of sine theta, so I'm going to take feedback from theta back to the acceleration, and it's multiplied by a negative value, so I'm going to use a gain right here, which is going to be negative g over L, negative g divided by L, and the feedback is actually sine theta, not theta. So what I'm going to do is insert a math function, a sine function, under math operations. Scroll down and you will find here trigonometric functions. In this block, if you double click, you will see that you have all the options, not just the sine. You have the sine, the cosine, the tan, and the rest of the trigonometric functions. I'm going to need the sine function, so I'm going to keep it as is and insert it right here. So now basically I have theta, and then I'm taking the sine of theta times negative g over L, and that's my equation of motion right here. I will add a scope to visualize the results. Okay. Now, let's assume that the length of the pendulum here is, say, 1 meter. So the gain will be negative g over L, that's negative 9.81 divided by L, which is 1 in this case. Okay. And let's run the simulation, play, and I will get nothing because there's no input and I have not defined any initial conditions. So what I'm gonna do here, I will start inserting initial conditions. I'll do external initial conditions, another external initial condition here. Okay, and then let me add constants to define the initial conditions. Here's the first initial condition to the first integrator, so this will be v0 or q dot 0. So I'm gonna call it dq 0, and then I need another initial condition. I'm gonna call it q0, theta 0 at time 0, and goes right here. So now here I have my complete model. Let's set the initial theta dot to 0 and the initial angle to 0.1 radians. And now let's run the simulation, and here's my sinusoidal response. I'll go to modeling and reduce the step size, solver details, and then auto, reduce it to 001. Run the simulation one more time, and as we see, we have a sinusoidal response starting from point 1, the initial condition, and you will notice that the period of oscillation is approximately 2 seconds, which is obvious since the omega squared is G over L, and the square root of G is approximately pi. So the period will be 2 pi divided by omega. That would be approximately 2 seconds. Now, the advantage of building the model in this way is I can now use nonlinear. I can model nonlinear equations that involve nonlinear functions such as trigonometric functions, whereas if we use a transfer function approach, we are stuck with only linear systems. Sometimes nonlinearity has major effect. To see the difference, I can compare this nonlinear model to the same model but using linear approximation. Let me duplicate the model here, copy and paste. Right here. Okay, and I will get rid of the nonlinear function. I will assume it's that sine theta is equal to theta. I will use the same initial conditions, Q0 and dQ0. Okay, let's take the output to the same scope and compare the results. Okay. See now, for small angle, the initial condition was 0.1 radians, and 0.1 is considered a small angle, so we can hardly see any difference between the two responses. But since my assumption to linearize the equation, the assumption was small angles, if I increase the size of the initial condition or the amplitude of oscillations, let's say 0.2, I should start seeing differences between linear and nonlinear models. You see the wave here starts deviating. Now I can see the lines were here on top of each other. Now the lines are starting to separate, indicating a difference in the frequency. The period has changed from one model to the other. Increase the initial angle a bit more, and now the difference is clear. The nonlinear model is the yellow model, and the linear model is the blue line. So the period of the nonlinear model is slightly larger than the period of the linear model, and that's due to the nonlinearity, due to using the sine function. So that proves that if I want to use a linear approximation, I have to make sure that the range of values of the angle theta, which I'm working with, is limited to small number, usually up to 0.2 radians. The difference is negligible. Here's 0.2. There's hardly difference in the frequency between the linear and nonlinear models. So this is an advantage of modeling systems in this way as opposed to transfer function approach. You can also set each model in a separate block, a separate subsystem. Okay, now here things look much better now. We can call this nonlinear and call this linear, and now have a clean model page, easy to read, and externally I only have the initial conditions.